Hey everybody, how's it going? So this video is going to talk about probability involving mutually exclusive events. So what mutually exclusive means is that the events that we are considering have no outcomes in common. So just for an example, if we talked about odd versus even numbers, those are mutually exclusive because there's no such thing as a number that is both odd and even. But if we talked about multiples of 2 versus multiples of 3, these are not mutually exclusive because, for example, 6 is a multiple of 2 and 3. Okay, just for one example. There are many numbers that are like that, but just to kind of talk about what the difference is between mutually and non-mutually exclusive. So when we are talking about mutually exclusive events, this is what my Venn diagram looks like because there is no overlap, and there's no overlap because they have nothing in common. Okay, so what we can do is we get this idea for a formula, the probability of A or B happening is just the probability of A plus the probability of B. Okay, so just keep in mind this symbol here means or. And the probability of A and B happening, so again, this is the symbol for and, is going to be 0 because there's no overlap, because there's no way that both A and B can happen. But if we have events that are non-mutually exclusive, that means that they do have something in common. And we get this formula here, which again, the probability of A or B is equal to probability of A plus the probability of B, so just like above. But now we're going to subtract that overlap. We're going to subtract the probability of them both happening. There is another variation of this formula. If we rearrange it, we could also say the probability of A and B is the probability of A plus the probability of B minus the probability of A or B. So basically these two things just switch places with one another. And this is what a non-mutually exclusive Venn diagram looks like. There's going to be some kind of overlap between them. So we're just going to do, again, some calculations with probability using some of these ideas here. We're going to think about whether things are or are not mutually exclusive. So example number 1, there are two 6-sided die that are rolled, and we have these events here. E is if we roll a sum that is equal to 8, F is if we get a sum that is equal to 4, and D is if we are rolling a double. So it says, write the outcomes for each event. So for E, well, that is rolling a sum of 8, so we could have 2 and 6. We could have 3 and 5. We could have 4 and 4. We could have 5 and 3. We could have 6 and 2. So there are 5 possible ways that we can roll an 8. For F, we have 1 and 3. We have 2 and 2. We have 3 and 1. Okay, there's no way that we can roll a 0, so there's no 4 and 0 option. Those are the only possibilities for a 4. And then doubles means both numbers are the same. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And also just an aside, but going back to set theory, if we were writing these things as sets, we would want to write them in curly brackets. We would want to separate each of our elements with commas. And I put brackets around it just to show that those are the outcomes of the rule. Okay, so these are my possible events, these are my possible outcomes for each event. So E and F, those ones are mutually exclusive because if we look at E and F, they don't have any outcomes that are in common with one another. And I mean, think about it logically, that makes sense. Is there any way that you roll two dice and you can get an 8 and a 4 at the same time if you add them together? No, because those are two completely separate sums. But E and D and F and D are not mutually exclusive because they do have an element in common with each other. So E and D, they both have a 4-4 outcome. F and D both have a 2 and 2 outcome. So these two events are not mutually exclusive because they do have something in common. Okay, I'm just going to write here because it does say D and E, but also D and F are also not mutually exclusive. All right, so that's just kind of a brief introduction into what mutually exclusive can look like when we are talking about an example. In example number 2 says integers from 1 to 15 are placed in a hat. If one slip of paper is drawn, find the probability that it is either odd or an integer larger than 8. Okay, so what I'm going to do first is I'm going to write the outcomes. So I'm going to call O my odd numbers. So my odd numbers are 1, 3, 5, 7, 9, 11, 13, 15. Integers that are larger than 8, so I'm going to call that E for 8. Doesn't really matter what letter you give it. So integers larger than 8 are 9, 10, 11, 12, 13, 14, and 15. And so just looking at these two lists, we can see that they do have something in common. They both have 9, 11, 13, and 15. So these are not mutually exclusive. Okay, but that's not what the question is asking. The question is asking, find the probability that the number we pull is either going to be odd or an integer larger than 8. Okay, and I'm just going to highlight here. So we have odd or an integer larger than 8. So we are finding the probability that a number is odd or it is an integer larger than 8. And just going back to our formula for mutually exclusive and non-mutually exclusive. So it is equal to the probability of getting an odd number plus the probability of getting a number larger than 8 minus the probability of the overlap, the numbers that are both odd and larger than 8. Okay, we have 15 total numbers. So that is going to be my denominator for each of my probabilities. I have 1, 2, 3, 4, 5, 6, 7, 8 odd numbers. So the probability of getting an odd number is 8 out of 15. I have 1, 2, 3, 4, 5, 6, 7 that are greater than 8. So that's going to be 7 out of 15. And then we're going to minus the overlap, minus the amount of numbers that are in both lists. So like I said, I have 9, 11, 13, and 15. So I have 4 out of 15 possible ways that we get a number that is both odd and larger than 8. Since all of my fractions have the same denominator, I can just add and subtract the numerators. So 8 plus 7 is 15. Take away 4 is 11 over 15. That's my probability of getting a number that is either odd or larger than 8. All right, example number 3 says a school newspaper published the results of a recent survey. So it's about students that are eating meals. It says 62% skip breakfast, 24% skip lunch, 22% eat both breakfast and lunch. So part A says, are skipping breakfast and skipping lunch mutually exclusive? So do they have nothing in common? And I mean, if you just think about it logically, the answer is most likely going to be no, because it is possible that a student could skip both meals, which means that there would be some kind of overlap between skipping breakfast and skipping lunch. But we can also prove it by adding these numbers together, because if we added these numbers together, they should add up to 100% because there's no other possible outcomes. So if we take 62% plus 24% plus 22%, that adds up to 108%. Okay, and we know that, well, hopefully know that with percentages, they can't go over 100%. So in this case, that would just mean they are not mutually exclusive. But now we're actually going to take a look at a Venn diagram. We're going to prove that there is an overlap between the two. So it says determine the probability that a randomly selected student skips breakfast but does not skip lunch. This doesn't have anything to do with the overlap necessarily, but we're going to prove it by putting these numbers into our Venn diagram. So I'm going to call this B and I'm going to call this L. Okay, so B is going to be skip breakfast and L is going to be skip lunch. Okay, so we know that the entire B circle should add up to 62%. The entire L circle should add up to 24%. But we also have this 22% that eat both breakfast and lunch. So they don't skip breakfast or lunch. So that 22 is going to go on the outside of our Venn diagram. So like outside of the circles. Okay? But what we can do is we can use the non-mutually exclusive formula to, well, I mean, what we could do is, one thing to keep in mind is that the probability of eating breakfast or lunch, if they were mutually exclusive, that would just be equal to the probability of eating breakfast plus the probability of eating lunch. Okay? Not eating breakfast, not eating lunch. So if this was 62 and this was 24, those add up to 86%. Okay. But we know that it can't be 86% because there are 22% that don't eat either meal. So instead of doing this, what I'm going to do is I'm going to use that alternate formula that I talked about, where we are calculating the overlap between the two. So instead of doing that, I'm going to calculate the probability of eating breakfast and lunch is the probability, skipping breakfast and lunch is the probability of skipping breakfast plus the probability of skipping lunch minus the probability of skipping at least one of the meals, at least one of breakfast or lunch. Okay, I'm going to come down here to part C to finish this particular example. So the probability of skipping breakfast is 62. The probability of skipping lunch is 24. And remember, we talked about this a little bit in the set theory unit. The probability of skipping at least one is we need to add up everything that goes into the circle. Now, we haven't done that calculation yet, but we know that 22% eat both breakfast and lunch. So what we can do is we can say, well, if 22% are outside of my Venn diagram, that means that 78% have to be inside of the Venn diagram. So if we do this calculation, we get 86 take away 78 is 8%. So this 8% is going to go into the middle of my Venn diagram. And then we know that the breakfast circle should add up to 62. So if we've already put 8 in the middle, there is 54% left over that skip only breakfast. And then lunch should add up to 24. We've already got 8 here. So there is 16% that is left over that skip lunch only. So what are we calculating? We're calculating the probability that a randomly selected student skips breakfast but not lunch. So that is this number right here. So that is 54%. All right, that's my number there. That is just in the B, not including the L. Part C says determine the probability that a randomly selected student skips at least one of these meals. So that is the probability of breakfast or lunch. So they skip at least one of them. And for that, we just add up all of our numbers that go in here. Like I said, that's just the inside of my Venn diagrams, which we've already calculated as 78%. All right, example number 4. Doesn't really have like much of a calculation to it. It's more of a, I think that is more of an opinion-based question, but we'll kind of go through it together. So it says Reed's mother buys a new washer and dryer for a set for $2,500, has a 1-year warranty. She can buy a 3-year extended warranty for $450. So then she'd be covered for any repairs for those 2 extra years. Reed researches repair statistics and finds the data in the table below should his mother buy the extended warranty. So it says for the washer, there's a 22% chance that it will break down and it'll cost $400. For the dryer, a 13% chance for $300 it would cost to repair. And for both of them to break down, there is a 3% chance and it would cost about $700 to repair both of them. Okay, so I'm just going to make a Venn diagram here, and we know that there's going to be overlap in this diagram because we have both as an option. So both the washer and dryer means there is going to be an overlap, and that overlap is that 3% chance. Now the washer is not 22% because we've already put 3% here, so there is a 19% chance left over that just the washer would break down. And we can do the same thing with the dryer. So the dryer's 13%. We've already put 3% in the middle, which leaves us with the remaining 10% that just the dryer would break down. Okay, so now again, there isn't really a calculation to this, but let's just think about each situation. So for the washer, just the washer, there is a 19% chance of that it will break down, and it will cost $400. But the extended warranty is $450. So the extended warranty is $50 extra than the repair. So it would be cheaper to repair it than it would be to buy it and have it covered under warranty. Okay, so we can do the same thing with the dryer. There's a 10% chance that just the dryer will that the dryer will break down, and it costs $300 to repair. So it is $150 more for the warranty than it is to repair it. So really the only way that it is worthwhile is if both of them break down, because if both of them break down, then you're covered by that $700 repair cost otherwise. But the probability that both are going to break down is only 3%. And so in this case, you would be saving $250. Okay, the 700 minus the 450 that it would cost for repair. So instead of spending the $750 to get both of them fixed, you would only be spending the $450 on the warranty, and it would be covered no matter what. So in this case, I would say it's not likely that both will break down. So I think in that case, I would say she should not buy it. But you can justify it any way that you want. All right, and we have one more example here. Example number 5 says a car manufacturer keeps a database of all the cars that are available for sale. For Model A, 43% have heated leather seats, 36% have a sunroof, 49% have neither. Determine the probability that Model A car has both heated seats and a sunroof. So this is going to be, we're going to calculate the probability of heated seats and a sunroof. So again, we talked about the variation of that formula before. That is just the probability of heated seats plus the probability of a sunroof minus the probability that it has at least one of those features. Okay, so what I'm going to do is I'm just going to draw a Venn diagram here. You don't have to do this if you don't want to, but I like to visualize where my numbers are coming from. So I'm going to use H for heated seats and S for sunroof. So we know that 43% have heated seats, so this entire circle will add up to 43. The entire circle for sunroof will add up to 36. And 49% have neither. So this 49% is going to go on the outside of my circles, because neither means they don't fall under either category, which means that my circles here in the middle should be adding up to 51%. So the probability that it has at least one of these features is going to be 51%. So this is the probability of at least one feature is going to be 51%. So we have 43 plus 36 minus 51. And if you do that calculation, that is 28% have both heated seats and a sunroof. So that's going to go in the middle. And then we can subtract to find what goes into the leftovers for each of these circles. So this one would be 43, subtract 28, which is 15%. This one would be 36, subtract 28, which would be 8%. So I would say the main takeaway from this lesson is, I mean, there's a nice refresher on Venn diagrams and how to make them, but I would say at least write down these formulas for mutually exclusive and non-mutually exclusive, as well as this variation of how to calculate the probability of both events happening.